Uh, Hi everyone. So let us slowly start today's session. So this is about week 7, and we'll be mostly talking about on few problems on Bohr-Sommerfeld quantization and some problems on uh, let's see on variational principle. So these are like last week we also did some problems on variational principle. So this week we'll be mostly focusing on 3D problems. Problems which has rotational symmetry, and then I'll end with some calculating of some scattering cross section. Okay, so that is the plan for today. And I am Ritojit Kundu, a PhD student at IIT Kanpur. So I am one of the TAs in this advanced quantum mechanics and applications. So yeah, so I'll start and I'll solve these problems one by one, and if at any point of time if you have any doubt, you can unmute yourself and you can ask. Okay, so I'll encourage you to ask questions during the session so that it will be helpful to you also. So is my audio clear, and video, can you see my screen also? Can anybody confirm? All right. Okay, so let us begin slowly. So this is about Bohr-Sommerfeld quantization. So so most of you probably have seen these results. You can arrive to this. So these results from WKB also. So the problem is, let's say you are given these potentials. Okay, so potentials which can be linear, and so in this case, this potential is like a ramp. Okay, and then you can have x to the power 4 potential. There are x to the power n kind of potentials. So this is a general case which will cover all of the above. And there you can also have potentials which has one of the side as a hard wall. This is called a ramp potential. Okay, so this can be linear, or this can be also some non-linear functions of a position. Okay, so generally speaking, all of these potentials you cannot actually solve by putting these potentials in the Schrodinger equation and try to solve those Schrodinger equation. So these things are not analytically solvable. So what we do is so there are two approaches to solve this. To get an estimation, we generally perform variational calculation. So in variational principle, what we do is we come up with a very good guess of the ground state. Okay, and if we'll plug that ground state at the ground state, we'll have some minimization parameter, and I will calculate the expectation value of the Hamiltonian in that ground state, in my proposed ground state. Okay, which might not be a very good one, and then we will try to minimize with respect to the variational parameter that is present in the ground state which we have chosen. So that will give us an estimate of the ground state energy, where this kind of estimation is bounded by the real ground state energy. Okay, so that cannot go below the real ground state energy of the system. So this is one way of estimating the how the ground state energy will look like. So but there is another way which is called Bohr-Sommerfeld quantization, through which we can get some idea, like we can get some analytical form of these energies. So we can answer many questions, like we can answer that how the energies depends on the this quantum numbers. Okay, so we can actually answer many of those questions which are otherwise we cannot actually tell from the perturbative calculations or from this variational principles. Okay, so let's look at some problems of Bohr-Sommerfeld quantization. So you are given some potential. So let's start with this first one, and you are asked to calculate the energy, okay, for this kind of potential. So like one of the main results of WKB is that we can actually, if we calculate this kind of quantity, this quantity is quantized. Okay, and this is so this was proposed many years ago, before the WKB approximation. But the WKB approximation actually modified it a little bit, and so added few corrections on top of that result. So which was before, initially it was called Bohr quantization. So now Bohr-Sommerfeld quantization is actually a better version of that, which takes account of the ground state energy, so the 0-point energy and all those things. So let's look at this first. So this is kind of a recap for you, I guess. So now if we have soft boundaries means that a potential something like this, so which is not going to infinity at whenever my particle is, so it doesn't go to infinity. Okay, so it's like a soft wall, soft boundary. If there is soft boundary and if I calculate this quantity for that system, I will get quantized values, but there will be a half. Okay, so this is you can also arrive to these results from WKB also, so which is covered in the class in the lectures. Now if you have one hard boundary, so other than having soft boundary, so one hard boundary means what? So let's say so this actually would look something like this. So one is infinity and another is some function of x. Okay, so this means this is a hard boundary. So hard boundary means the boundary where the potential actually blows up, it goes to infinity. Okay, and at hard boundary you know that this wave function should be 0. Okay, so for hard boundaries this quantity PdQ integration should be similar, but there is a little term which is different from the previous term. So this is 3/4 rather than being 1/2, this is just 3/4. Okay, and if you have both hard boundaries like what you do in particle in the box, so something like this, where in both of the boundaries actually blow up, so in that case we should get something like PdQ is NH. So here H is the Planck's constant. So yeah, so let us first look at this one. Okay, so where the U is given by F modulus X. So let us look closely at this potential. So if that is the potential, so how it would look like? So now let me plot it. So if this is your x-axis, and you know the mod functions look something like this. Okay, and so if you take the tangent, so if the tangent so if this is the theta, so tan of theta will give you f, because this is a linear potential, so tan of theta will give you f. So that's how the potential looks, right? So first of all we'll have to make sure that, okay, I mean if I want to calculate some quantity using these formulas, I have to make sure that that kind of potential actually supports a bound state. Okay, so what do I mean by that? So now let me give you another potential, something like this. So let's say so I'll give you something like let's say this. Okay, so let's say this is a potential which is minus x square. So this is something like minus x square. Okay, so you see that this actually doesn't support any bound states. Like, so this can, so if a particle comes from any one of the side, it can scatter and it can go to different directions depending on what is the exact form of the potential, but there is no bound state. So for bound state, it should be something like this. So it should have a valley. Okay, so only potentials which has valleys, like this one has a valley, only those potentials can support bound states. Okay, because particle can get stuck into here and the state can be only here, so those are the bound state. Okay, so but this kind of potential which looks like a bowl, right? So that doesn't actually supports any bound state. It can give you different scatterings, but doesn't support any bound state. So first of all you have to make sure, okay, to go on with these calculations, the potential that we are talking about must have to support bound states. Okay, so now if that is satisfied, now let's say I want to calculate energy which is around here. Okay, and you know that where the energy cuts the potential, so these are called turning points. Okay, so why it is called turning point? Turning point because at exactly those points your momentum becomes 0, and you can think about a classical particle. Okay, so a particle which actually goes here, at that turning point it loses its velocity. Okay, and when it loses its velocity, it actually comes back and it also tries to go along that path, but at that point it loses its velocity, it loses its momentum, so it again comes back to the valley. So you will have some kind of oscillation. in this kind of potential. Okay, so these are the turning points. So turning points has the property that momenta is zero. So uh, so uh, so what you want to do is you want to find out that what are the turning points. So if I can find that out, that will set the limits of the integration. So in this case, so let's solve for this. E is equal to f x. So I'm writing the turning points as x bar. Okay, and there used to be a p square by 2m, but at turning point this is 0. So now I can solve for x, right, x bar. So x bar will give me e and f, e by f. So x bar is plus minus e by f. So these are the turning points for this kind of potential. Okay, so let me denote those points here. So this is minus e by f and this is plus e by f. Okay, now let's look at that integration. So p dq, okay, and there is something like this, so which means that I have to go back and forth between these turning points, and then only I'll be able to get n times h, right? I guess, yeah, that is correct. Okay, so I'll have another half, so n plus half h. Okay, so now let's try to write this integral with proper limits. So then I will have minus e by f to e by f, and remember it is actually coming back and forth, so I have to multiply 2 because for each of the trajectories, and then p dq is n plus half h. Okay, so now let's write our energy. So energy is given by p square by 2m plus v of x, right? So now from this equation we can find the momentum, solve for momentum. So p, you can find out the p, which would look like 2m e minus v of x. Okay, so it will have plus and minus value, but let's stick with the plus value. Now we can plug that thing here in place of p, so it becomes 2m e minus f and mod of x. Now let me write in place of dq dx. Okay, so it is just I am changing the dummy variable from q to x, which is totally legal, minus e by f to e by f. Okay, now you see, okay, so there is a square root which I am missing. Now you can see that this integrand is actually an even function, and I have symmetric limits. So what happens to this even function? Now that gives me additional 2, so this the factor becomes 4, and I will have 0 to e by f 2m e minus f times x dx. Okay, so now I have to just perform this integration. So before doing that, let's try to extract all of the dimensional full quantities from the integration. So I mean, you will understand what I mean by that in a moment. So let's say I'm taking few things common. 2m e, I can take that common because e is a constant, e is a number which gives you the quantized energies. So e I can take out of this integration. Then I will be left with only this part. Okay, so now let's do another change of variable. So change of variable, I want to make this whole quantity as a new variable, so that I don't have to bother about these constants here and there. So y is x divided by e by f. Okay, so that means that I can directly replace this with y. Okay, but then I'll also have to change my limits and dx. So dy becomes dx by e by f, and also my limits, so x and y. So x had limits 0 and e by f, so now y will have limits from 0 to 1. Okay, so I'll now put all of this information back to this integration. So okay, so there is, so remember that there is always this n plus half h on the right hand side. Okay, all right, so let us just substitute all of those things that we just calculated. 0 to 1, 1 minus y square root, and in place of dx, so dx becomes e by f times dy. So I'll just place that here, so it becomes e by f. Okay, so m, so e to the power, so I'll now have e to the power 3 by 2 and by f. Okay, so now you see that I have extracted all of the dimension full quantities from this integration. Okay, so now this whole quantity is just a number. So this kind of integrations you can find out from some standard integration table. Okay, but the physics of this whole equation doesn't actually depend on that simple factor. Now if you want to qualitatively argue that how does E depend on n, okay, how does E depend on some function of n, actually up to this is all right, you don't have to perform this integration. So let's first see. So before that, just so let me elaborate on that part, that so I started with this integration and I did some manipulations. I took something out of this integrand and I did some change of variable to extract all of the dimension full quantities like E, F, all of those things out of this integration. Okay, so now all of the dimension is stored in this expression. Okay, and now I am only left with a number. So this integration doesn't depend on any other variables which are present in the system. So this is just a number, and for qualitative argument we don't have to even calculate this number. So what do I mean by that? So let's just let's just see this. So this means that e to the power 3 by 2 is actually proportional to n plus half h. Okay, so because let's say I want to know how does this e depends on the n, so that then you can just do this manipulation and it becomes n plus half, and let's also forget about h, so 2 by 3. Okay, so like this is all of the physics in these two lines. So these constants here actually doesn't matter. So if you want to just ask, okay, how does the energy depends on the quantum numbers, this is how it depends on the quantum numbers for a linear kind of potential, f mod x. Okay, so this is the answer you want, but let's say you're not satisfied with that, also you want some quantitative numbers. Okay, so now to solve this kind of integrations, which you will see for this kind of WKB calculations, so let me provide you with a little integration identity, so which is again in terms of gamma function. So gamma function during this kind of calculations becomes very handy. So it will just, I mean, if you replace any integrations into these forms, it will give you answers directly. Okay, so now what do I have here is, so I have 1 minus x to the power n, okay, and m. So this gives me some gamma functions, gamma 1 plus m and gamma 1 plus 1 by n, and in the denominator I have gamma m plus 1 by n plus 1. Okay, so during I mean using this formula, you have to just be aware of the fact that here this n sitting here has to be greater than 0, only then this formula is valid, and also m sitting here should also be greater than -1. So other than these cases you cannot actually use this formula. So now let's identify let's identify these things. So what is our n here? So n is just 1, okay, and m is just half. Okay, so I'll in place of this thing I'll just plug in gamma 1 plus half. So this is gamma 1 plus m, gamma 1 plus 1, so n is 1, then gamma 1 plus half plus 1. Okay, so this is the whole results. So let's simplify this gamma function a little bit. It becomes 3 by 2, it becomes gamma 2, and then it becomes gamma 5 by 2. Okay, so as you might be aware that the gamma functions are nothing but these factorials. Okay, but for fractional numbers this is not a factorial. For fractional numbers it will be something different, but for integers this is just a factorial. So this in the numerator it becomes half square root pi, and then gamma 2 is just 1, and in the denominator it becomes 3 by 2 half and square root 2 pi. Okay, so here I am using the fact that gamma z is z minus 1 factorial. Okay, and gamma half is square root pi. So you can obviously cancel few things from bottom and top, so then you are left with 2 by 3. Okay, so this whole integration will just give you 2 by 3. Okay, so this is just a number, and we'll calculate how explicitly the energy depends on this n. So 4 square root 2m e to the power 3 by 2 f times 2 by 3 is n plus half h. So you take all of those things on the right hand side, so it becomes 3 f by 4 square root 2 m n plus half h to the power 2 by 3. I hope I am not missing any constants here. So like this is how the energy depends on the quantum number. Okay, so but in contrast, so when you have done for harmonic potential where you have half m omega square x square, so that means, so just look at the factor of x square. So look at how the algebraic dependence of position here. So for this you can also perform the same business, but you know because you have already solved for the Schrodinger equation using potential, this is nothing but n plus half. Okay, some h bar omega is also there, but it depends linearly. So energy here depends linearly, but energy in this case actually depends on some n to the power 2 by 3 for large n. Okay, so that is the biggest difference between the harmonic oscillator and this linear kind of oscillator, linear mode oscillator. Okay, so is this clear? Any questions? All right, so if there is no question, so I'll show you some other problems for this WKB also. So let us also try to okay, so there is x to the power 4, which I will leave for you to do. Okay, so I'll rather do x for x to the power n. Okay, so x to the power n is the most general thing you can have, and I'll be using again the identity of this Green's function to save few calculations. So let us do that, and I will encourage you to do this problem in the same manner. Okay, or you can solve this directly and plug n is equal to 4, you will get the right answer. Okay, so okay, let us do for n is equal to yeah, so all right, so our potential is now given by f of u is equal to f and mod x to the power n. Okay, so mod this, so that means that this potential looks something like this. So there is some x to the power n sitting here, mod x to the power n. Okay, so here also we first see that can we have bound states or not. So clearly, because this is a upside down, this is a normal kind of bowl, so we see that okay, it actually supports bound state energies. Okay, so then we proceed to calculate the turning points. Okay, so turning points in this case will be like similarly like we have done in the last case. So x bar mod to the power n. So now I will solve for x bar to the power n. So it becomes e by f to the power 1 by n. Okay, so now I know, okay, so this turning point is actually given by minus e by f to the power 1 by n and e by f to the power 1 by n. Okay, so these are the two classical turning points, and Now, and so also my momentum is given by square root 2m e minus u of x, which is just f, and mod x. So this is my momentum. So let me just take this 2m e out of this thing, so it becomes 1 minus x to the power n by f by e by f. Okay, and now let's calculate this quantity pdq. So in this case also, because these are soft boundaries, this will become n plus half h. Okay, so let us again so proceed in the same way. So let's write the limits of this integration. So the limits will become e by f to the power 1 by n and e by f to the power 1 by n, and because it has to go back and forth, which is represented by this circle on this integration, so there is additional 2. Okay, because it has to cover the trajectory, so it has to like go and come back. Okay, and I'll write 2m e 1 minus x to the power n e by f dx. So the main principle, if you start with the main principle, I mean, you should be okay. So these algebras might be you might get stuck at some point, but these are just simple algebras. So if you are getting stuck at some integrations, you can look up some tables of integration, then you will be able to find out that standard form, and then you should be okay. Okay, but you should always remember this first principle, that one should start with this. If one wants to evaluate the energies, one should start with this and take all of these constants out of this integration. Okay, that will tell me the dependence of the energy on the quantum numbers. Okay, so now okay, so before doing that, so I can, again, this function is even function, so I will just make this limit between 0 to this e by f to the power 1 by n. So dx. Okay, so now let's do some change of variable. So I want to call y to the power n to be x to the power n by e by f. Okay, so I am again reducing it to the standard form, so which means that so d y to the power n minus 1 dy is n x to the power n minus 1 dx by e by f. So I want to find the value of dx. So this n from both hand side will cancel, and dx will be given by e by f times y by x to the power n minus 1 and dy. So that is my dy, and let us find out our y by x from this thing. So y by x is given by okay, so 1 by 1 by e by f to the power 1 by n. Okay, so yeah, what do we have here? So dx times e by f, and so y by x is 1 by e by f n minus 1 by n. So let's simplify this constants by e by f, and on the to the power there is 1 minus 1 by n. Okay, so now you see that this will actually cancel with this 1, and so now dx will end up with dx is e by f to the power 1 by n. Okay, so I am taking it to the numerator, so the minus becomes plus times dy. Okay, So after doing this algebra, you found your dx, which we want to replace by dy. So now let us just, okay, and also the limits in this case, like previously, so these are 0 and e by f, okay, and so here also it will become 0 and 1, okay. So yeah, okay, so 4 square root 2m e 0 to 1 minus y to the power n square and dx, and there are additional terms such as e by f to the power 1 by n, okay, and on the right hand side we have n plus half h. All right, so now again, so like this is just a number, okay, but let's just evaluate it. We'll be using the same identity here also. So here, so n is just n, right, so is just n and m is half. So the formula for this part was like gamma 1 plus m, so 1 plus half, gamma 1 plus n, and gamma 1 plus n plus half. So this is the formula. So we can try to simplify this little bit. So it becomes half square root pi n factorial, and so n plus half. Okay, so because there is a half sitting here, we cannot actually write in terms of factorial, so let's not do that. And then we are left with 4 2m e times e by f to the power 1 by n times this constant. Okay, and this quantity should have to be equated to n plus half h, right? So now let's, so we can do this algebra and find out the exact expression for the energy, but let us try to do something a little different. So we'll just want to find the dependence of energy on the quantum numbers. So E1 plus, so half plus 1 by n, okay, is proportional to the, to let's say n, okay, linearly let's say. And okay, so actually I should be a little bit careful here, because okay, yeah, so yeah, we have to be a little bit careful here. So this is actually different index, so let me call it p, okay. So this is some different integer which is different from m and n. All right, so now so we're asking that, okay, how does this energy depend on the p? So you just do this algebra and you write down n plus 2 p to the power 2n by n plus 2. So this is the most general result that you can have, okay. So you can actually check back whether your last result, so for which you have done for the linear potential where n is equal to 1, so for n is equal to 1, you can see clearly that this becomes p to the power 2 times 1 and 1 plus 2, so p to the power 2 by 3, okay. So this actually matches with the result. So p here is integer, the quantum number, okay. So for n is equal to 2, it should give us a linear, right? So so let's check that also. 2 times 2 by 2 plus 2, okay. So 2 times 2 is 4, so this is just p, okay. So you get a linear. So this is general result. So now if you have, so and if anybody gives you some potential which is like algebraically to x to the power n, so you directly know that what is the how do you so what is the dependence on the quantum numbers, okay. So yeah, so this is what I wanted to talk about in this WKB. So you can actually do a few more examples to get yourself familiarized with this kind of problem. So for example, So we have done where we have soft potentials, right? So potentials which are not diverging on any of its boundaries. So you can actually also do for this ramp potential, which has one boundary which diverges, which is infinity, and one which is some polynomial function of x. So you can do this for a general fx to the power n. So like we have done here. So but remember that in this case you have to write pdq. So okay, so remember in this case we will have to use this formula. Instead of using n plus half, you'll have to use this n plus 3 by 4. Okay, but if you want to qualitatively argue the dependence on the this quantum numbers, this numbers actually doesn't matter. Okay, you can directly calculate what is the dependence on quantum numbers. So this is related to some problems in your assignment of week 7. Okay, so I hope you have gotten an idea of how to do this kind of calculations. So let me do one more calculation in this regard, which is like this Coulomb potential. Okay, so we'll have Coulomb potential, and we'll be using Bohr-Sommerfeld quantization to find out what is the energy dependence of this potential. Okay, and we should be able to find out it should be as 1 by n square. Okay, because that is the exact expression for energy for a hydrogen atom. Okay, so let us look at this one problem. So any questions, any confusions? So please feel free to ask. All right. So let us look at this problem. Yeah. 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 So like in this case, one boundary is going to infinity. So when it goes to infinity, we say that okay, this is a hard boundary. So this boundary is a hard boundary. So in this potential, one boundary is hard and one boundary is a soft boundary. Okay, so in this case, yeah, yeah. No, it doesn't matter. So any polynomial functions, any well-behaving functions is a kind of a soft boundary. Okay, so anything which doesn't go to infinity instantly. So like this will go to infinity obviously at some infinity, right? But it doesn't go to, if we are looking at some ground state, it doesn't matter. So any function which doesn't go infinity immediately, that is a soft boundary. That is a, okay. Okay, non-linear function, yeah. Yeah. Yeah, so that is what we are trying to figure out. So it actually depends how the energy depends on n, or so let's say n to the power z. So that actually depends on what kind of potential you are given. So if you are given a linear potential, you will have different behavior than a non-linear behavior. Okay, so you know from when this potential is proportional to x square, the energy should go as n. Okay, but for most other cases you do not know. So this WKB, or this Bohr-Sommerfeld quantization, gives you one way to estimate okay what can be the dependence of it. Okay, or how does the energy grow with the this quantum numbers. So like for linear, it will be different, and this will be different. So this depends on the power. What is the power of this? What is the polynomial behavior? What is the exact polynomial? It depends on that. How the energy will grow. Okay. Okay, so any more questions? All right, so let us do this Bohr-Sommerfeld quantization for this Coulomb interaction. Okay, for hydrogen atom basically. So again, so we'll have to first see that okay. So and we are taking that L is equal to 0, right? So because this hydrogen atom, each of the eigenstates has LM coordinate, LM quantum numbers. So we are saying that okay, this L part is actually 0. So if that L part is 0, that actually takes away the centrifugal force which is present in your Hamiltonian and makes our life a little simpler. We can do simpler calculations. Okay, so let's say angular momentum L is equal to 0, and so our Hamiltonian, or let me write the energy as some p square by 2m plus, so ur, which is just z e square by r. Okay, so again, so this is like, so this potential is something like this. Okay, so yeah, there should be a minus here. Yeah, there should be minus here. So the potential is something like this. Okay, so this is your r. Okay, and so r goes from 0 to infinity, and we see that okay, if the energy is negative, so there are bound states. Okay, but for positive energy there can be no bound state. There can be scattering, obviously. So let's say, as we said before, that this formulation is valid only for bound states. So so let's say that we are in a bound state. Okay, so E is 0. Now if E is 0, so now I can also try to write this as some minus mod E, so that to precisely tell that this is actually a negative energy, this is actually a bound state. So minus mod E, and this is the same as p square by 2m minus z e square by r. Okay, and here also you want to find out what are the turning points. Okay, so we see that one turning point is sitting at 0. Okay, so turning point 1 sitting at 0, and one turning point is sitting at somewhere else, so let's call it to be A. Okay, and at the turning point momentum is 0. Okay, so then we can actually find out the turning point, the expression for the turning points. So then I will have mod E minus is equal to minus z e square by r. Okay, so yeah, so I am replacing r by a to get the expression for the turning point, and this minus cancels from both hand side. So a is given by z e square by mod of energy. Okay, so this is my one turning point, and the momentum is given by, like as usually, it is given by 2m and E minus v of r. Okay, so yeah, so it is just like 2m, so E, I'll be replacing it minus mod E minus z e square by r. Okay, so this is my momentum. Yeah, I am missing a square root. So this is how the momentum looks. Okay, and then we want to calculate this integral p dq, and let's so because we want to argue that what is the dependence of n. Okay, let's say we are taking the just n pi. Okay, in this case just n pi. Okay, the half or 3 by 4, it is not really that essential for qualitative arguments. So let's just write this integration. So now the integration limits are set by 0 and a. Okay, and because it has to go and come and back, right, so that's why there should be an additional 2. Okay, so now let's put all of these integrations. So it becomes z e square by r mod e, okay, and minus 1 half dr. Okay, so I am taking 2m and e out, but I am leaving the minus there. Okay, so the minus is left there, so minus 1 I have written as the second part of this equation, and then I am left with z square by e and r. Okay, so now let's try to do a little okay, little manipulation to these things, a little massaging to this equation. So now I'll use the expression of the turning point and I'll replace inside the integrand. So this becomes a by r minus 1 to the power half dr. Okay, So I have just replaced that. Okay, this part is nothing but the expression of A, right? So that's what I am using. Now let's try to do a change of variable. So let's just write x. Let's introduce a new, call our new variable as x, and which is a rescaled version of the radius r by a. So dx becomes dr by a, and the limits, they become quite simpler. So r and a, r and x, so it was 0 and a, and now it becomes 0 and 1. Okay, so this kind of scaling always helps to bring that integration into some let's say standard form for which we know the results. So I'll just use that here. So there is one a sitting here, and it becomes 0 to 1, 1 by x minus 1 to the power half dx. So this kind of integration is it is easy to do this kind of integrations using something called contour integration, which you will learn in complex analysis course, but we are not going to go there. So I'll give you the identity for this. So this is nothing but just pi by 2. Okay, if you calculate this integration, you'll find this is nothing but pi by 2, so n pi. Okay, so now let's try to simplify things a little bit. So I'll use the expression of a, which is z e square by modulus of e, and then I have pi by 2, which came from the integration. Okay, so now let's try to simplify things a little bit. Okay, not n pi, nh. Yeah, so this is nh. So 2 square root 2m mod e. So let's cancel this 2 with this one. Z e square is nh. So let's keep e on this side. 2m, 1 by z e square, it becomes 1 by nh. So e mod, let's say square root, I am still keeping the square root, z e square by nh, and square root 2m. And if I just take a square in both of the left hand and right hand side, you will see that you get some 4m square z square e to the power 4 n square h square. Okay, so there are many things in this expression, but the most important part is the energy is proportional to 1 by n square. Okay, right? So which is the case for hydrogen atom. So like you see, for with very few line of calculations, we could actually found out the dependence. We didn't have to solve the whole Schrodinger equation, whole matching wave functions, and so many steps we have actually avoided in this. But we have got a sensible result that the energy depends on 1 by n square. Okay, so yeah. So any questions? Which part do you want me to repeat? Huh? Yeah. Right. Yeah. So so I understand what is the confusion. So okay, let me draw it a little bit clearly. So now here we have a minus 1 by r kind of potential, right? So this is my r axis, and this is my minus 1 by r, and minus 1 by r, and yeah, so this is my minus z square by r. Okay, so now this pdq and this whole integration is actually only valid for bound states. Okay, for only bound states you can these formulas are valid. So for this kind of potential, which is which is totally negative, so where we can have the bound states, so the bound states will be somewhere like here. So this is a typical bound state. So where the energy is something like negative, minus mod E. So this will give you one of the bound state, right? So there will be many bound states. So but let's say we're looking at a single one of the bound state. So let's say this is the bound state I'm looking at, and if I have correctly identified the bound state, from that information of bound state I can actually find out the classical turning points, okay, so which set the limits of the PDQ integration. So you see that here even if the potential actually goes to infinity, I mean for like zero energy there is no turning point at all, but for some negative energy one of the turning point is this 0, okay, and one of the other turning point is this, which I am calling as A, okay. And A, if you plug in if you use this expression for turning points, you will see that A is nothing but Z square by energy. So this is how I found out the turning points, and then I set the limits of this expression, which is right now between 0 and A, okay. So now the rest part is to do do algebra, do some calculations, do integrations. So that is the rest of the part, but the main intuition is to finding where the turning points are, okay. So this is the first thing that you have to find out. So is that clear how I am finding the turning point here? So for finite energy the turning points are not at infinity, but at zero energy, at exactly zero energy the turning point is at infinity. So there is no bound solution at that energy, so there can only be scattering at that energy, okay. So is that clear? Okay, all right, so let us move on. So yeah, I wanted to okay, so where are we? Okay, so let us actually look at this part. So this is similar to some of the problems which are there in the assignment 7. So what we're looking at scattering cross sections, but we're looking at under the first Born approximation, okay. And so I have come up with a few examples that what can be the potential, okay. And so this is a result from scattering theory, that if your potential is actually a symmetric potential, so that it doesn't depend on the direction of the of your x, y, z, it depends only on the modulus. So R is just the modulus. So this is like central field problem that you do in classical mechanics. So if this is the form of the potential, then for that the scattering cross section is given. The scattering cross section you can simplify a lot, okay. So the scattering cross section that consists of the scattering potential, which is given by this V function, and there is the sign QR, which is from the outgoing waves matrix product elements. So this is the integration that we have to do, okay, to find the scattering cross section. So now let me show you illustrate some examples how you can do that. So we'll be using this formula throughout, okay, and we'll be just plugging in these functions and we'll do the integration, okay. So let us do the first one. So the first one is V is just Z E square by R. So d sigma d omega is 4m square h bar to the power 4 q square, and then I have to do the integration 0 to infinity r prime z e square by r prime sine q r prime, okay. So most of these things here these are constant, so we'll think about them later, but let's just focus on this integration for now. So we see that this r prime actually cancels from numerator and denominator, so we are left with only this part 0 to infinity sine q r prime dr prime, okay. So this is the integration you have to do, right? So we know that this integration sines and cosine, this integration will give you actually cos, okay, for a finite kind of limits, okay, but for infinity it is not very clear what it should be. So let me show you a trick how to do this kind of integration, because these are converging integrations and these are some value. So let me write this sign as imaginary part of e to the power I q r prime, okay. So this is nothing but sine 0 to infinity imaginary part of e to the power I q r prime dr prime. So let me keep that imaginary part out of this integration. Now I can actually introduce a small parameter here. Limit delta tending to 0 to infinity e to the power I q plus I delta and r prime. Okay, so this delta at the end of the calculation, I'll take this limit of delta to be 0. So now, so just to give you some insight why I'm choosing like that, so let's look at this exponent. So this exponent is nothing but e to the power iq times e to the power minus delta times r, right? So you see that there is actually an decaying part sitting in this integration, sitting in the numerator. So even if this is oscillatory, there is a part which is sitting, which is like decaying part. Okay, so as the r tends to infinity, but still the delta is 0, so then this part e to the power minus delta r prime is actually becomes 0, right? So then it allows us to perform this integration explicitly. So now okay, so after that is done, so let us just do this integration. So limit delta tending to 0, and then there is 1 by, so this is just like any normal exponential integration, so it is just e to the power I q plus I delta r prime, and in the downstairs we will have I q plus I delta. Okay, and we'll have to set the limits from 0 to infinity. Okay, so at infinity, obviously this whole thing is 0. Okay, so the limit we have to set is just the lower limit. Limit delta tends to 0, and then there will be minus coming from the second term, and I q plus I delta. Okay, so I can actually send that I upstairs to cancel this minus. So now let's take the limit of delta tending to 0. So now it becomes I by q, right? And the imaginary part of this, because q is a real number, so imaginary part of this thing is just 1 by q. Okay, so just to write the result, so the result of this integration 0 to infinity sine q r prime dr prime is just 1 by q. Okay, so given that this q is actually a real number. Okay, so this is the result of the integration. Now let's use this result and plug into this equation. So d sigma d omega in this case is given by 4 m square by h bar to the power 4 and q square. So there will be some other constants, z e square and q square. So because this is a mod square sitting here, so that's this integration just we're writing as 1 by q square, right? So in the q in the scattering theory is given by 2k sine theta by 2. Okay, so you plug that back at the end. So now this will give you 4 m square h bar to the power 4, so z e square to the power 4, and q square is okay, so q to the power 4 is in the downstairs, so it will become 2k to the power 4 sine theta by 2 to the power 4. Okay, so this is the scattering cross section. Okay, so this is actually the result which was obtained by Rutherford. Okay, so this is also called Rutherford scattering. So I mean, this is a very useful tool I mean, to check a hypothesis. So let's say I am saying that, okay, let's say I have a system, I have some kind of quantum system which has this kind of interaction. So like here I am saying that, okay, this has 1 by r kind of interaction. So what I'll do is I'll perform these calculations, and I'll have some result, right? So now what I'll do is I'll go and ask my experimental friend who can actually perform the experiment in the lab. I'll ask him to do the same experiment, and I'll take those two results. One is which is the analytical calculation done by me, and the other is the experimental result which is performed by some experimentalist. So then I'll try to match these up, and I'll see if they match. Then I'll say, okay, my theory is actually correct. Okay, but if they don't match at all, then I'll say, okay, the interaction which I was thinking the system has, the system doesn't have that. So let's start from a different kind of interaction, and let's try to find a good fit to the experiment. Okay, so this is how the experiments are done. Okay, so yeah, so this is I mean really very useful. And yeah, and in particle physics experiments, this is the main crux of the computations. Okay, so yeah, so that was something about yeah, something about scattering cross sections. So let me show you another example in this regard. So this is, now let's say I am saying that okay, I am giving 1 by r square. Okay, it is the inverse square potential. So Coulomb interaction is just 1 by r. So this is something something, let's say I'm giving you which is 1 by r square. So let us try to do this integration for 1 by r square also. So for 1 by r square, let us directly look at that integration. So d sigma d omega is given by some number 4m square and h bar 4 q square, and then there will be some alpha square, and there will be some the integration. Okay, so let me do that integration actually. So the integration here is given by 0 to integration square. So integration is given by r prime. So v has 1 by r square, r prime square, and then there is sine q r prime and d r prime. Okay, so we see that one r actually cancels, so we are left with 1 by, okay, sine q r prime and q r prime. So yeah, r prime. So again, so this is not a very, I mean so you can do this with contour integrations or complex analytical methods, but let us try to let me give you a simple identity to use. Okay, so let's say you have sine of x by x integration ranging from 0 to infinity. Okay, so the result of this is just pi by 2. Okay, so now we'll try to reduce this integration into the same form. Okay, so it becomes 0 to infinity sine q r prime. So I'll multiply 1 q downstairs and upstairs, so it becomes dq r prime. Okay, you see right now my dummy variable is just q r prime. Okay, so I mean this is reduced to the standard form, and this is just pi by 2. Okay, so this integration doesn't depend on q at all. So if I have 1 by r square kind of interaction, 1 by r square kind of scattering potential, then this integration doesn't depend on q at all. So I'll be only left with d sigma d omega 4m square alpha square, and then there is just pi by 2 whole square. Okay, so then you will replace q with 2k sine theta by 2. Okay, square alpha square pi by 2 square, and then it becomes 1 by 2k sine theta by 2 square. Okay, so like in the last case when the potential was just 1 by r, we obtained that this depends as sine to the power 4 sine, but in this case for 1 by r square it only depends as this kind of thing. Okay, so this is scattering is this is absolutely necessary to check your hypothesis, check your theory, right? Check your particle I mean check your theory, how much consistent it is with the experiments. Okay, so yeah, so that is how you do this sort of calculation. So there is another example that I thought one should do. So you can start, I'll leave this example for you. Actually you can start with this kind of interaction where the r is just linear, right? And you can try to do these integrations. Okay, you can see if you can do that integration, and try to write a scattering cross section within the first Born approximation. Okay, so I'll leave that for you. So up to this point, is there any question, any doubt? Okay, so if not, then yeah, so these are the things that I wanted to talk about. So first one is the WKB approximation and the scattering cross sections. Another thing I wanted to talk about, but yeah, so which is about the variation principle in 3D. Okay, so which I think let's cover that next time, or in the last week also we talked a lot about variation principles. So you can look into the last week's video which is uploaded in the YouTube, and you can try to figure out, okay, how to do this for hydrogen atom. This will be a good practice for your for to do some variational principle calculation in 3D. Okay, and specifically this problem is you can also find this out. I have worked this out in the week 7's this session's presentation, which is uploaded in the folder which you have access to. And this session is also recorded, and you will have access to this session also in case you want to go back and check some of the things. Okay, so if there is no, so is there any questions? So if there is no questions, so let us finish this today's session. So next we will talk a lot more about scattering cross sections. Okay, so yeah, so that will be all for this week, and I hope you have a good weekend. Okay, I'll see you next week. So yeah. Okay.